You can't hear her, but a mother is crying over her 2-year-old child. The child died of dehydration a few minutes ago from a final bout of diarrhea. A family is by a dying 60-year-old man. They don't see it, but we would say he is a small man whose health has never been good. Both child and the man were born in communities where infant life is dangerous. Inadequate nutrition, waterborne disease, or poor sanitation and hygiene habits may cause death or lifetime poor health. Every day, 1,300 infants die from diarrhea alone. More than 20% of the people in the world suffer from poor health and productivity for these same early childhood causes that arise from ignorance and poverty. You may not be able to change the whole world, but you can certainly make a difference. Providing safe drinking water to infants is a significant reduction to child danger. The membrane module shown can be used in a number of arrangements to separate waterborne microorganisms from contaminated water. If you and a few others raise a loan of Australian dollars 1,000, it will provide one of these arrangements to make a difference in a Timor-Leste community to improve the lives of hundreds of people over the next few years. There is no guarantee of repayment, but there is every hope that the community be able to repay the loan and future maintenance from savings in health costs and improved productivity. This is a gesture of friendship that Australians may be said to owe to East Timorians. But beyond friendship, we gain, as any action that reduces poverty reduces the otherwise widening gap between rich and poor. That in turn leads to terrorism and global warming. If you are interested, we can later discuss communities you may wish to support. But for now, let me tell you about the hardware. The drawing illustrates a hollow fiber membrane module. The hollow fibers are made from membrane materials that allow clean water to pass through the fiber walls, but block off dirt particles, bacteria, and larger microorganisms. During filtering, a valve at the end of the hollow fibers is closed, forcing clean water to flow out of the valve on the outside of the module. If the clean water discharge valve is closed and pumping is continued, clean water accumulates in the pressure tank. Opening the valve at the end of the hollow fibers allows the clean water compressed in the pressure tank to backflush through the walls of the hollow fibers and scours out the particles in the hollow fibers. Closing this valve and opening the clean water discharge valve recommences filtering. Picture shows the ends of the hollow fibers. The working arrangement will need some form of pre-screening to avoid blocking the hollow fibers, which have an internal diameter around 0.9 of a millimeter, that is 900 microns. Picture of typical raw water and treated water. Treated water output in the arrangement shown later may be from 180 to 400 litres an hour, depending on the module type and the amount of solid particles in the raw water, i.e. turbidity. Most of our projects will be with communities where poor sanitation will contaminate rivers, ponds, or shallow wells with fecal material, otherwise known as shit. The H2S strip test is a simple test which can identify the presence of fecal matter in water within 2 days. If there is fecal material in the water, the sample will turn black. Otherwise, it will remain a light brown color. The pictured module was recently installed in Arnhem Land in an indigenous settlement. An overhead tank gives enough water pressure for both filtering and backflush. Pre-filtering is before the overhead tank. As with all of the arrangements discussed, this is a point of use arrangement intended to fill users' containers. This picture is a kit for similar sites where raw water supply level is high enough to give pressure for both filtering and backflushing. A pressure limiting valve prevents excessive pressure inside the module. This arrangement would be used where the tank height or elevation of a river intake is 10 meters or more above the filter. If the elevated tank or river elevation is around 6 meters, there will be enough pressure for filtering, but not enough for backflush. In this kit, a hand pump replaces the pressure limiting valve to charge the pressure tank for backflush. This video shows an arrangement where the raw water level is below ground level. In this case, the pre-filter is a wedge wire screen attached to a float, so intake water is fine colloidal material that will not block the hollow fibers. Oversized floating material is easily removed from the surface of the pre-filter by movement of the water or by a light brush. The video illustrates filtering, pumping into the pressure tank, discharging from the pressure tank, and then going back to filtering. The color difference between the treated water and concentrated wastewater is very obvious due to the high concentration of particles in the high turbidity raw water. The module is capable of producing safe drinking water from raw water of such high turbidity. However, the amount of water used for constant backflushing will considerably reduce the useful output. Some form of chemical dosing may be warranted to reduce such high turbidity prior to the membrane module. In this arrangement, pressurized raw water is supplied from an electrically operated pump. Pre-filtering is standard sediment filter with cleanable filter element. Valves are electrically operated, controlled from a 12-volt PLC programmer to the same sequence for filtering, pressure tank compression followed by backflush and then returning to filtering. Picture identifies main components where electric controls replace hand-operated valves. Picture identifies valves which control the operating pressure in the module. Operating pressure in these units is preferably around 60 to 80 kPa to avoid rapid fouling of the membrane hollow fibers.